This is Physics 2220, Lecture 2, and today we're going to talk about electric fields. So, last time we learned a little bit about electric forces and Coulomb's law. So the electric force is a field force, and field forces can act through space. The effect is produced even when there's no physical contact between the objects. For example, gravity is a field force. Last semester you learned about gravity and how there's this force between, say, the Earth and the Moon. There's no physical contact there, but there's still a force. Well, Faraday developed the concept of a field in terms of electric fields. So let's go back and look. A gravity field is said to exist in the region of space around a mass. So, if I took a mass somewhere near, say, the Earth, it's going to fall in the direction of the arrows, fall towards the center of the Earth. The G field, or the gravitational field, is the gravitational force divided by the mass of whatever the test object is, or the force per unit mass. That's the little g that we've used all last semester. So, an electric field is said to exist in the region of space around a charged object. And that charged object is going to be called the source charge. When I have another charged object, we'll call it the test charge, and it enters this electric field, there's an electric force that acts on it. The electric field is defined as the electric force on the test charge per unit charge. Like the gravitational field was the force per unit mass, now we have a force per unit charge. And then we have the electric field vector, which we'll use E for our electric field. And that electric field vector at a point in space is defined as the force acting on a positive test charge, with charge Q naught, placed at that point divided by the value of that test charge. So the electric field is the electric force divided by the charge. So E is the field produced by some charge or a distribution of charges separate from the test charge itself. The existence of the electric field is a property of the source charge. The presence of a test charge is not necessary for the field to exist. So this test charge then serves as a detector of the field. Just like in gravity, if I had a mass above the surface of the Earth, that mass would be a test mass. It could prove that there was a gravitational field because when I released it, it would fall. But whether or not that mass was there, the gravitational field would still exist. So then there's a relationship between force and electric field. The electric force an object field is equal to its charge times the electric field in the region where it exists. Now this is valid for only a point charge. A point charge, remember, has zero size. For larger objects, the field may actually vary over the size of the object, and so it would become more complicated. Now, if the charge that is creating the field is positive, then the force and the electric field are in the same direction. If the charge is negative, force and electric field are in opposite directions. So the direction of E is the same as the force that would occur on a positive test charge. So if we look over here, we see this charge distribution. It's creating an electric field. If it's positive, and I had a positive test charge, we know that like charges repel each other, so this object is going to go in this direction. So that would be the direction of the electric field. The SI units of electric field are newtons per coulomb. So we can also say that an electric field exists at a point if a test charge at that point experiences an electric force. So if we remember Coulomb's law and apply that between the source and test charge, remember Coulomb's law said the force, the electric force is K times Q1 times Q2 over R squared in the direction along the line between them. So if we divide out Q naught, the value of our test charge, the electric field of a point charge is then just force over Q is going to be KQ over R squared in a radial direction away from that point charge. So again, direction of electric fields. In figure A, we see that Q is positive, and F then is directed away from Q for a positive test charge. So in B, we see then at point P, regardless of that test charge being there, there is an electric field and it points radially away from the test charge, from the source charge. In C, of course, if we had a negative charge distribution, that test charge would be attracted towards it, so the force would be towards the source charge. If we take that away at point P, then there is an electric field that points towards the negative source charge. So electric fields point away from positive charges and towards negative charges. Now, the electric field is a vector quantity. So at any point P, the total electric field due to a group of source charges is equal to the vector sum of the electric fields of all the charges. Mathematically, we write this, that the electric field is K times the sum of the Q over R squareds in the different R directions. It might look like a complicated equation. It's just a vector equation. I figure out the electric field due to each individual source charge and calculate what it is at a certain point, and the net electric field is just the vector superposition of all those electric fields. Or in other words, the electric field is KQ1 over R1 squared in the R1 direction, plus Q2 over R2 squared in the R2 direction, and so on and so forth. I just add each one up vectorially. So for example, if I wanted to find the electric field at this point P, the first thing I would do is figure out the electric field at point P due to this positive charge at Q1. And then I would find the electric field at point P due to the negative charge. And of course, E2 is going to point in this direction. E1 points away from that. Then once I've done that, to figure out the total electric field, I just add those two like vectors. Now that works great for point charges, but there are a lot of times where we don't have point charges. We might have a continuous charge distribution. Maybe I have charge throughout a volume or over the surface of a sphere. So the distances between the charges in a group of charges can be smaller than the distance between the group and the point of interest. If that's the case, we can model the system as a continuous charge distribution. The system of closely spaced charges is equivalent to a total charge that is continuously distributed along some line or over some surface or throughout some volume. So how do I figure out the electric field due to a continuous charge distribution? Well, let's look over here at this blob of charge. What we're going to do is, instead of worrying about all this charge, we're going to look at a very small piece of the charge. We'll say its charge is delta Q. So we're going to divide this charge distribution into small elements, each which contains that same delta Q charge. Now, we can calculate the electric field due to just that small little element of charge. And then to figure out the total electric field at point P, I need to figure out the electric field due to all the delta Q's over the entire charge distribution. So for each individual charge element, the little bit of electric field, which we'll call delta E, is just K times the charge, delta Q, over R squared in the R direction. Now, because this charge distribution is continuous, I can let this delta Q get smaller and smaller and smaller. And in fact, we'll let it go to 0. And that just gives us the definition of an integral. So the electric field then becomes the K times the integral of dq over R squared. But remember, this is a vector integral because as we move around and look at different charges, that vector r may change, and so we'll need to pay careful attention on how to do these integrals. Be thou not afraideth of dq. We're used to seeing things like dx or dy when we integrate. How do I integrate over charge? Well, there's a relationship between a distance and a charge that we're going to use to make these integrals something that's more familiar. So in order to do this, we need to introduce something called a charge density. Density, you might remember, is mass per volume. It's just telling you how much mass is packed into a certain volume. Charge density is something similar. Only instead of mass per volume, it's going to be a charge per volume. So a volume charge density is if I have a charge distributed evenly throughout a volume, then the volume charge density, rho, is the total charge over the total volume. Of course, I can also have charge over a surface, and then I'd get something called a surface charge density. So when that charge is distributed evenly over a surface area, the surface charge density, sigma, is equal to the total charge over the total area. Or I might have charge continuously distributed in a line or along the surface of an arc, or the curve of an arc. Then I'll get a linear charge density. So when charge is distributed along a line, lambda, the linear charge density, is the total charge over the total length of the line. So then if I look at a little bit of, say, the volume charge, the little bit of charge is equal to rho times a little bit of volume. Or on a surface, the little bit of charge is equal to sigma times a little bit of area. Or along a line, the little bit of charge is equal to lambda times the length, the little bit of the length of the line. So we can use these if I'm integrating over, say, a volume charge density. Wherever I see dq, I just replace it with rho dv. And dv is something we understand. We can integrate over a volume. So dq is rho dv, which would be rho dx, dy, dz if we were using Cartesian coordinates. Or maybe we're going to use spherical polar coordinates. So dq would be rho times r squared sine theta, dr, d theta, d phi. We can use either one of these when we want to do this integral. So, some hints when solving these problems. First, make sure of your units. When using the Coulomb constant K, the charges must be in coulombs and the distances in meters. Next, calculate the electric field of any point charges. If we could use the superposition principle, find the fields due to all the individual charges as at the points of interest, and then add them as vectors to find the resultant field. If, however, I have a continuous charge distribution, the vector sums for evaluating the total electric field at some point are replaced with vector integrals. So we divide the charge distribution into infinitesimal pieces, calculate the vector sum by integrating over the entire charge distribution, and of course, if there's any symmetry, we got to take advantage of that symmetry to simplify our calculations. So how is this done? Let's look at some examples. Let's say I have a charged rod. It's got a length L, and it's got a uniform charge density lambda. Remember, that's the total charge divided by the total length. So we're going to look at a little segment dq here, blue, that's got a little segment length dx. We want to find the electric field at point P. So we start with the idea that dE is equal to k dq over r squared. In this case, we know that the electric field, due to all the little pieces, is going to point in the minus x direction. So we don't have to worry about direction here. We don't have to worry about the direction of the vectors. All we need to worry about is the magnitude. So the total electric field, of course, is just going to be the integral of dE, which in this case is going to be k times the integral of dq over r squared. So here, since we're integrating over a length, we can replace dq with lambda dx. So now the electric field is k times the integral of lambda dx over r squared. In this case, r squared is just x, because our electric field, the point of interest, is at the origin, where x equals 0. And then our limits of integration are when x equals a to x equals a plus L. Of course, the lambda comes out of the integral as a constant, and the integral of dx over x squared is minus 1 over x. And I have to evaluate that at my limits. So I plug in my limits, so I get the electric field as k lambda. I get minus 1 over a plus L plus 1 over a. I need to find a common denominator. If I do that, I get a plus L minus a over a times a plus L. The a's go away. And the electric field is k lambda L over a times a plus L. But I also remember that lambda times L is just the total charge. So lambda L I could replace with just Q, the total charge on the rod. So then the electric field would be KQ, or K lambda L, over A times A plus L, and the minus X direction. Well, let's look at another problem where we actually have to worry about the direction of the electric field. So let's have a ring that's got a radius A and has a total positive charge Q on the ring. Find the electric field at a point at distance x from the center of the ring along the axis of the ring. In other words, I look along the axis of the ring at distance x. I want to know what the field is at this point. So we start again with the idea that the magnitude dE is equal to k dq over r squared. That dE is due to this little bit of charge up here. We're looking at a piece of the ring, the dq. And the magnitude of dE is in this given by our equation, but it's got a certain direction. It's pointing kind of down and to the side. But now let's look at this. As I go at look at the little charge at point 1, the electric field points off in this direction. But when I get down to point 2, the electric field is going to point up in this direction. Now remember, we need to add all these vectors up. I'm going to add all the way around, but let's just look at these two pieces that are opposite of each other. Each of these electric fields I can break up into a part that's along the axis and a part that's parallel to the axis. So this would be dE1's component along the axis and perpendicular. Well, dE2 is also going to have a component along the axis, but it's got a component in this direction too. And these two are equal in magnitude and opposite in direction. So the perpendicular part of the electric fields cancel out, and that's going to be true no matter what 2 points on that as I go all the way around the ring. So I'm figuring out the electric field now as I go around the ring. So from the symmetry of this problem, I can ignore the perpendicular part. All I have to worry about is the electric field along the x direction. Now, the electric field then in the x direction is just the magnitude of that vector times the cosine of theta. This is just like taking the components of any vector that we did last semester. The component in the x direction is the magnitude of it times the cosine of the angle. We're just breaking this up. And if we look at this triangle here, cosine of theta is this distance x divided by r, where r is the distance between the charge and the point of interest. It's the same r that we have up here. R is the square root of a squared plus x squared from the Pythagorean theorem. So now, the cosine theta is x over the square root of a squared plus x squared. So, dEx is k dq over r squared times cosine theta, which was x over r. So this is going to be kx dq over r cubed, or kx dq over a squared plus x squared to the 3/2 power. So then the total electric field in the x direction is just the integral of dE sub x. So it's going to be the integral of kx dq over a squared plus x squared to the 3/2 power. So now, how do we do this? Well, let's look at this integral real carefully. What is constant in this integral? Well, k is just a Coulomb constant. X, as we're integrating around dq, the distance x doesn't change. And the radius a is also a constant. So x's, a's, and k's are all constants and come out of the integral. So then I'm just left with the integral of dq. In this case, I don't need to worry about converting it to using a linear charge distribution or anything like that. I'm just integrating dq. And if I add up all the little bit of charges all the way around the ring, I'm going to get the total charge on the ring. So then the electric field is kxq over a squared plus x squared to the 3/2 power. Or the electric field at that point is kqx over a squared plus x squared to the 3/2 power in the x direction. Now, one of the things we might want to do with electric fields is try to visualize them. And electric field lines give us a means of representing the electric field pictorially. The electric field vector E is tangent to the electric field line at each point. So the line has a direction that is the same as that as the electric field vector. The number of lines per unit area through a surface perpendicular to the lines is proportional to the magnitude of the electric field in that region. So the more lines, the stronger the electric field. The density of lines through surface A is greater than that through surface B in the picture on the right. The magnitude of the electric field is greater on surface A than surface B. And the lines at different locations point in different directions. That indicates that the field is non-uniform. So let's look at field lines from different point charges. From a positive point charge, the field lines all radiate outward in a radial direction. In 3 dimensions, of course, it would be spherical. They're all directed away from the positive source charge. And then we can see that if we were to place in any position over here a test charge, it would experience a force that would go away from that positive source charge. For a negative point charge, the field lines are also radial, but they point inward in all directions. They're all directed toward the source charge. So if I put a positive source charge out here, it would accelerate towards the negative charge. Now, one of the ideas that pops up in electric fields is something called a dipole. A dipole is when I have two charges that are equal in magnitude and opposite in charge. the number of field lines leaving the positive charge is equal to the number of field lines terminating on the negative charge. They'll all come out right close to the charge radially outward, but then they will form this dipole pattern of electric field lines that we see on the right. If I have two like charges, I get a field distribution as shown on the right. Here the charges are equal and positive. The same number of lines leave each charge since they're equal in magnitude. Now, if I were to look at this and expand this out and look very far away, at a large distance the field looks very much like that of a single point charge that has a total charge of 2q. Of course, I could also have unequal charges. If I have a positive charge and a negative charge, the positive charge in this case is twice the magnitude of the negative charge. So we have two lines leave the positive charge for each one line that terminates on the negative charge. And if I was a far distance away, the field lines would look approximately the same as a single charge of plus q. So, rules for drawing electric field lines. The lines must begin on a positive charge and terminate on a negative charge. In the case that we have an excess of one type of charge, some field lines will begin or end infinitely far away. The number of lines drawn leaving a positive charge or approaching a negative charge is proportional to the magnitude of the charge. And at no point can we have two field lines cross. So what does the motion of a charged particle look like? When we have a charged particle and it's placed in an electric field, of course, it experiences electric force. If this is the only force on the particle, it must be the net force. And the net force causes the particle to accelerate according to Newton's laws. So we know that the electric force is Q times the electric field, and that has to equal m times the acceleration of the charge. So looking at this vector equation, we see that if E is uniform, then A is constant. So if the particle had a positive charge, its acceleration is going to be in the direction of the field. If it has a negative charge, the acceleration is going to be opposite the direction of the field. And since the acceleration is constant, the kinematic equations could be used. So here's an example of an electron in a uniform field. Say I have an electron that's projected horizontally into a uniform electric field. So I have some device that's got a positive charge on one plate, negative charge on another plate. That's going to cause the electric field to go from the positive to the negative in a uniform manner. As the electron moves in, it's going to experience a force towards the positive charge. And that's going to be a constant force. And the parabolic path that it takes is going to be identical to that of a ball in a gravitational field. There's lots of devices that we can make using these ideas. And one that used to be very popular and is dying out now is something called a cathode ray tube. So CRT was commonly used to obtain visual information in oscilloscopes, radar systems, old television sets, the tube sets. The CRT is just a vacuum tube where we have a beam of electrons accelerated and deflected under the influence of electric or magnetic fields. So here I have the schematic of a CRT. I have some device here called the electron gun. Essentially I just have an electric field between a cathode and an anode, and it causes electrons to accelerate, and there's usually a hole in the anode so the electrons go shooting off. And then I have vertical and horizontal deflection plates. I just create an electric field on either one. It's going to cause the beam to move left or right or up or down. And by varying these, I can cause the electric beam to go across, or in a case of a television set, it would raster back and forth like this across, and then again, and then again. I would do that 30 times a second. And there's phosphorus on the screen, so every time an electron hit, it would cause it to glow. Or in the case of a color television, there would be red, blue, and green phosphorus, and you have a certain amount of electrons that hit each little piece of phosphorus that causes those colors to fluoresce. So let's review what we talked about today. The first thing we talked about today was the electric field. What an electric field is, it's the force per unit charge. The electric field of a point charge is kq over r squared, or if I have a charge distribution, I use the magnitude of the little bit of field due to a little bit of charge is k dq over r squared, and then I would integrate it to find the total charge. And then last we talked a little bit about electric field lines, how to visualize electric fields in space.